So 15.5, just we're going to do an introduction to parametric surfaces. All right, so we have we've worked with parametric equations for curves in the plane and in space, both as parametric equations and as vector valued functions. We can think of both of those as types of parametric equations. We're going to do something similar with surfaces. So for curves, we had a single parameter. Usually we use t. Sometimes we use theta if we were in using polar coordinates. And for surfaces, our parametric equations are going to be functions of each component of our set of equations is going to be a function of two variables. So let me draw some parallels here. So we have curves. For curves, we have several ways that we can describe a curve. We have the explicit form. And that's what we see most often, just y equals f of x. So that's our explicit form of a curve. We can also write our curve in implicit form. And that's when we have some f of xy equals 0. And then we had our parametric or vector form. Where we had r of t equals some x of ti plus y of t j. For surfaces, we have several ways that we can talk about surfaces. A couple of them that we've talked about already. And then we'll talk about the parametric ones today. So we have explicit, our explicit form for a surface. And that's when we wrote our equation of our surface as z equals some function of x and y. And implicit form is when we said that f of x, y, z equals 0. So that's our implicit form. For a parametric form, what we're going to talk about today, we have some vector function of u and v, and we have each component is some function of u and v. Yes. Thank you. So this is our parametric form for a surface, and we're saying f, g, and h are continuous. They're well-behaved functions in some region of the u-v plane. So u and v are just our parameters. So we're going to we say r of u and v is a parametric surface. And f, g, and h are parametric equations for the surface. So this is how we're going to describe our surface parametrically. And what we're going to do with a parametric description of a surface is, one, we're going to get familiar with visualizing parametric surfaces. That's what the point of the lesson today is. And then we're going to use this definition of a parametric surface to come up with the idea of a surface element on a surface, a little ds. And then we're going to use that little surface element to do integrals over the surface of various kinds of functions. So that's where we're going with what we're doing. Couple of important things about parametric representations of surfaces. They are not unique. So we could find multiple parametric representations for a particular surface. To sketch or to visualize a parametric surface, we want to try to eliminate a parameter or find some kind of relationship between the x, the y, and the z component to come up with a familiar equation. And we've done something like this before when we work with parametric equations for curves. With surfaces, because we have the extra variable, it's just a little trickier. So we're going to visualize we try to eliminate a parameter or see a relationship between the components. Sometimes we can just look at our representation and see some kind of relationship. Finding parametric equations for a surface is usually kind of difficult. Some exceptions are if we have spherical and cylindrical coordinates. We have some experience using spherical and cylindrical coordinates, and those would be a type of a parametric surface if we describe them with spherical or cylindrical coordinates. Or if z is some function of x and y, we have this explicit form for a surface. So some of the ones we're familiar with, paraboloids, spheres, hyperboloids, those kinds of things. If we have the quadric surfaces, something that we're familiar with already, then our parametric representation or aparametric representation of the surface would be r of x, y. Our parameters are just x and y. Would just be xi plus yj plus f of xy k. So if we have our explicit form in rectangular coordinates, this would be a parametric representation of a surface. And we can do something similar with cylindrical and spherical coordinates because we know what each component, how to represent each component in terms of r theta or r theta and phi. So questions on what we're doing, or what the big idea that we're talking about today. All right, so I have some graphs here. And we want to match the surface with the graph. So this is out of your book. It's on page 1105 if you have your book. If you want to look in your book, you can follow along here. So what I want to do here is just practice visualizing these surfaces, or practice coming up with a visualization for the surface. So for number one, we have this is our parametric surface, ui plus vj plus uvk. So what relationship between the components can we see right away? I'll give you a hint. I'm going to say z equals uv, and u is x and v is y. So z equals x times y. So we can see that relationship right away. So which surface would that be? That would be C. If we think of a constant z, so if we have xy equals 1, those are hyperbolas. Xy equals 2, hyperbolas. So for a constant z, we're going to get these hyperbolas on the surface here. So this would be C. So this one, it was easy to see the relationship between x and y. How about number 2?
A.
And it says A. Let's
D.
D. So what makes you say D?
Well, I can see that so based on the x and y components, we should get some kind of circular base.
Okay.
But at the same time, it's multiplied by u. So as you increase the value of u, the more and more rotations, what will happen is the base will get wider and wider.
Okay. So the cosine v and sine v suggest some kind of circular thing, and we're multiplying by u here. So Ahmed kind of thought logically about what the surface would look like. How could we? So that's a very good way of visualizing. It is D. How could we come up with a representation or a relationship between the x and y and z components here? What do we like to do with sines and cosines? Square them and add them together. So if I say x squared plus y squared, I get u cosine squared v plus u sine squared v. What does that equal? U squared, which is z squared. X squared plus y squared equals z squared. And that, we know, is the equation of a cone. So that would be D. How about 3? What did you say? Ahmed thinks B. So what I would suggest with number 3 is, well, we still have the sines and the cosines and u's and v's. So what do we like to do with those? Square them. So x squared plus y squared is going to be 4 cosine squared v cosine squared u plus 4, what do we have? Cosine squared v sine squared u. And I can factor out a 4 cosine squared v. So that just equals 4 cosine squared v. And z equals 2 sine v. So z squared equals 4 sine squared v. And I get x squared plus y squared plus z squared equals 4. And that is a sphere. So that one took a little more work to find the relationship between the x's and y's. And then for the last one, that leaves, what are we left with? A. And to analyze this last one, I would square x and y, so I get x squared plus y squared equals 16 for any value of z. So we get a cylinder. So that would be A. So questions on those examples? Yes.
For number 3, it kind of looks like they're converting into spherical coordinates instead of
No. So that would, so what we've done is basically written the spherical coordinates instead of in terms of theta and phi, in terms of u and v. So that it is exactly the conversion from rectangular to spherical. Yeah.
Is that a hollow cylinder?
Yes.
Why is it hollow? Oh, it only equals 16.
Right. It only equals 16. So we're just getting this.
Yeah.
And for any value.
Does it matter at all that v equals v?
No, we could say it's just saying x squared plus y squared is 16 no matter what z is.
Okay.
So for any z, you're going to have that circle at that level. So we just have the cylinder just building up as we increase with z. All right. Let's look at a couple of others. Rather than matching with the surface, we're going to convert from a parametric form to rectangular to an explicit form and describe the surface. So what if we want the rectangular form. R of u and v, our parametric surface is ui plus vj plus v over 2k. So what relationship do we see here between our components? What's that? Z equals v over 2. So in terms of x's and y's, z equals y over 2. So if I rewrite this, I can say y equals 2z, or y minus 2z equals 0. So what kind of surface is that? That's a plane. We just have a linear relationship between y and z. And yeah, for any value of x, we have y equals 2z. Questions on that one? So we're just doing something similar to what we did with parametric equations for curves, just trying to relate our parametric equations to something that's familiar to us. R of u and v for this one is 2u cosine v I plus 2u sine v j plus 1/2 u squared k. So what's going to be our relationship here? X squared plus y squared is going to be, if I square x and y and sum them, what do I get? 4u squared. And that is related to z out equals 8z. So x squared plus y squared equals 8z. And what is this surface? What is it? Paraboloid. So in each of the coordinate planes in the YZ plane, we have 8z equals y squared, we get a parabola. In the xz plane, we have 8z equals x squared, so we get a parabola in both those planes. And for a constant z, we get circles. So we have a paraboloid. Let's do one more, a little trickier. So our parametric surface is 3 cosine v cosine mu I plus 3 cosine v sine u j plus 5 sine u k hat. So what are we going to want to do here? Square the x's and y's. So x squared plus y squared is going to be 9 cosine squared v. Now what do we want to do? Square z. So z squared is 25 sine squared. Did I say v? This should be v. There we go. Z squared is 25 sine squared v. So how can I write this as a surface that we're familiar with? What's that? What you said? An ellipsoid. So I could say x squared plus y squared over 9 plus z squared over 25 equals 1. And we have an ellipsoid. So sometimes we have to kind of think a little, be a little clever when we're working with these to find the relationships. All right, questions on those? All right, the next ones that I want to do, I want to look at a surface and the parametric representation of the surface, and then we're going to look at some other equations and decide how the surface is going to change if we're representing the surface in terms of these other equations. So let me grab that one. Let me grab my other problems. All right, so here's our surface. We have, this is our parametric representation of the surface, u cosine v plus u sine v minus u squared k. And we end up with this paraboloid. We just looked at something like this, similar to this, just a minute ago. I'm sorry. This is our surface. U cosine v I plus u sine v j plus u squared k. So that's our surface. This is our paraboloid, and we just worked through one like this. We want to decide how these different equations, if we represent the surface with this new parametric equation, this new vector value function, how is the surface going to change? So what is number 9? We have u cosine vi plus u sine vj minus u squared k. What's that going to do to it? Flip it upside down. So we're just turning the z's negative. So this is going to be flipped.
Okay.
This is on page 1105 again, number 9 through 12. So it's going to flip or reflect over the xy plane, I guess we could say. Number 10, we have u cosine bi plus u squared j plus u sine b k. So we're just switching around some of the components. So how would this change it? It would rotate it, right? So what's going to be the axis of our paraboloid now? The y-axis. So the axis would be the y-axis. The I-axis? How about number 11? We have u cosine bi plus u sine bj plus u squared k. The equation is the same, but here we're graphing from u equals 0 to 2, v equals 0 to 2 pi. Here we're graphing u equals 0 to 3, and v equals 0 to 2 pi. What is it? Just going to make it taller, right? We're just graphing it a little higher up. The z's are bigger, so this is going to be taller. And then our last one, 4u cosine bi plus 4u sine bj plus u squared k. Make it wider, right? So if we let z be a constant, our circles are going to have a bigger radius. So this is going to be wider. So questions on those? Okay, I just want to do one more example where we have a rectangular representation of a surface. A couple of examples where we have a rectangular representation, an explicit representation of our surface, and we want to find a parametric representation. I'm trying to do some examples of all the different kinds of ways that we want to think about these. All right. So we want a vector value function or a parametric representation. For the plane x plus y plus z equals 6. So what can we do with this? What are we going to want our parameters to be? Just, well, we don't want sine. If we had some kind of circular surface, we might want sines and cosines. Oh yeah, if they were squared, that would be great.
If we isolate the...
Okay.
If let's say we made x equal u, y equal v, we could isolate v, or we could see that it's 6 minus u.
Okay, and rather than saying, we could say x equals u and y equals v, why don't we just let our parameters be x and y? Okay? So then we get z equals, so you had a good idea, z equals 6 minus x minus y. So I can say r of x and y is, what did you want to do from that? X I hat, y j hat. Perfect. And we said this right at the beginning, if we have z equals f of x, y, then this could be a parametric representation of our surface. So that one not too bad. Questions? All right, let's look at one that's a little trickier. So first off, what kind of surface is 4x squared plus y squared equals 16? Ellipse. So it has something to do with an ellipse. a cylinder with an ellipse as a base. So we don't have any z here, so it's not an ellipsoid. So for any z, we're going to have this ellipse, this elliptical shape. So what would be a easier way to represent this ellipse? How do we normally write the equation of an ellipse? First let's write it in rectangular coordinates. What's our standard equation for an ellipse? X squared, divide everything by 16, so x squared over 4 plus y squared over 16 equals 1. So there's our standard equation for an ellipse. So now let's parameterize. How do we normally parameterize an ellipse in the plane? So x equals 2 cosine u, we'll call it. Y equals 4 sine u. And z equals, this is u. And z equals v, anything. So there are our parametric equations. So we're going to say that r of u and v is 2 cosine u I plus 4 sine u j plus v k. And there's our parametric surface. So just a new way of thinking about surfaces, representing surfaces. What we'll do tomorrow is use parametric representation of surfaces to come up with a way of describing a little element of area on a surface, and then we'll use those to do surface integrals. So that's where we're going with this parametric surfaces. All right, and your homework. Shouldn't be too taxing.